Hi guys, we were discussing about capacitor and its capacitance. So just recall what is a capacitor? Capacitor is a device which consists two parallel plates. So if I draw symbol for capacitor, so capacitor symbol just two parallel plates. So these are the connecting wires. Now the capacitance of a capacitor, first we derived capacitance C equal to Q upon V, charge per potential difference, and later we converted this expression in terms of capacitance C equal to epsilon naught A upon D. So here A equal to area of the plate and the D equal to separation between the two plates. So this you can take as D, and the epsilon naught equal to the medium between the plates. Epsilon naught we are terming as permittivity. Now the capacitance of a capacitor can increase by, if you can increase area, so C can increase by increasing area of the plate because they both are proportional, and the C can decrease, or if you take C can increase by decreasing the distance between them, and C also proportional, capacitance is also proportional to permittivity. It means if you can keep between the plates some other materials, especially which are having electric field like like dielectrics. If you can keep a dielectric material between the capacitor plates, so the capacitance of capacitor also increases. So that concept we will learn so in further classes. So if I can decrease the separation, so if I can take capacitance graph it here. Now the capacitance of a capacitor, if you can decrease the area, so first I need to apply the potential. Now the capacitor is fully charged. Now if we can increase the separation or the decrease the separation, the capacitance value will get vary. Now the capacitance of a capacitor is purely depends upon the arrangement what we make. If we can increases or decreases the area plate and the separation distance between them, so that affects the capacitance value. So let me here itself can explain. Suppose if I take this is a dielectric, so if I can keep this dielectric between the plates, so let me take and the capacitance, but I will explain this concept later. So if we can keep the dielectric medium between the plates, so without the dielectric, here we can see there is the capacitance value, so 0.89 times 10 power 13 minus 13. Suppose if we can keep this dielectric material, so now the capacitance value is increased to 4.43 times 10 power minus 13. So this concept I will make you understand later, but today's my concept is, so not either increases or decreases the capacitance value, but still if you are having multiple capacitors with us, so if I am having so many capacitors, but I cannot increase the capacitance area or decrease the capacitance. So if I combine capacitors, this combination can be done in the two ways. So that once we can call series combination, second we can call parallel combination. So what is series combination, parallel combination? Suppose if I have it here, now this is the already capacitance showing the capacitance of a capacitor 1 times 10 power minus 13 farads. Now if I connect two capacitors in series, means if you take this is the capacitor symbol, and if you connect one more capacitor, so in series means, so We need to connect end to end connection, so this we can call end to end. It means one hand of the capacitor, or we can precisely say in terms of the leg, capacitors are having the two legs. So in the two legs, one leg should connect as another leg of the another capacitor. So if we draw that for the series combination, if I take three parallel plate capacitors, so here I'm having an option to select as three in series. So in series, if you can see, the one end of the capacitor is connected to another end. So this is a capacitance C1. If you can take this as a 1 and this is 2 for the capacitance C1. So for the capacitance C2, that is the first plate and this is the second plate. For the capacitance C3, first plate and the second plate. Now the second end of the first capacitor is connected to as a first end of the second capacitor. Unlikely, the second end of the second capacitor is connected to first end of the third capacitor. So in the circuit manner we can represent like this. So if capacitor first plate and this is second plate, the second plate should connect as another plate. So likely we should connect via a potential difference. Here the potential difference I can represent that as a battery. Now this combination we are calling series combination. Now if it is series combination, if I take the capacitance of individual capacitors, so here each one having the capacitance of 1, so this is the capacitance value 1 times 10 power minus 13 farad, 1 picofarad. Now if you can all having the 3 or having the 1 each picofarad. Suppose if I can apply the potential difference, the capacitance gets charged. Now if I want to know what is the total capacitance, if I take it here the total capacitance meter, so now here you can see the meter shows that the total capacitance of this combination. So this is the total capacitance of the combination equal to, here it is showing 0.33 times 10 power minus 13 farad. Now if you can observe, this is the total capacitance of the three in series combination, which is less than individual capacitance. So here the individual capacitance C1 equal to C2 equal to C3 equal to 1 picofarad. Now if you connect capacitors in series, the resultant capacitance value decreases. Again I am repeating, if we connect capacitors in series, the resultant capacitance or the total capacitance value decreases. So we need to see that in terms of the mathematical expressions. So let me take the mathematical expression set here. Suppose if I draw the capacitors, let me take heading as capacitors in series. So for that I am taking three parallel plate capacitors. So this is the first plate and second plate of the first capacitor. So let me connect this with conducting wire. Let me take one more plate. Now if we can make connection between that, now if I connect this one is capacitors of C1, it is C2 and it's capacitance C3. And if we connect that to a potential difference of cell, so this cell having the potential difference is V. Suppose if we on this, so it is positive potential. Now this plate gets positive charge, and this is now the electrons will start to move from this opposite direction. So this is the direction of the electron, but if we will represent only the direction of current, so the direction of current is always opposite to the direction of electrons. So that is the direction of the current in the circuit, but the electrons always will move opposite to the direction of the current. So that's the convention we are following. So if the electrons follow like this, so this is the direction of electrons. The green arrow mark which I am representing in the circuit, that shows the direction of electron. Now these electrons will reach us, and this plate will accumulate negative charge. So the charge flows from first plate to another plate. Now since it is a negative plate, due to because of the induction, so this plate accumulates positive charge, and likely here this plate will accumulate inside negative charge, and this plate will accumulate again positive charge, and this plate accumulate negative charge. Now each plate, you can see each plate having both positive charge and negative charge. So if we can highlight this in between, so this is the first capacitor which is having the one plate with positive charge and the another plate with negative charge. So this is the second capacitor, it is also having the same one plate positive charge, another plate negative charge. So the third capacitor, the first plate having the positive charge and second plate having the negative charge. So if I take the charge on this here for calculations, it is the plus q, and this is the equal charge of the minus q. So here the plus q and here is the minus q, the plus q and here it is the minus q. Now we need to derive the mathematical expressions for that. So in series, first we need to see what is the potential difference between the capacitor plates. So if I connect the voltmeter between it here, so for the first plate, so the voltmeter shows the V1 is the potential. For the second plate, if we can connect like that, so if we can connect one more voltmeter in the second plate, so the potential difference between the plates is decreases. So because since it is connected in the series, so the total potential what we applied, so V is the applied potential. So that is the key expressions in this series. So if you can write that total potential V equal to sum of the individual potentials. So V1 plus V2 plus V3. So this is happens in the series combinations. So in the series combination, the potential difference between the two capacitor plates is different. So that we can see with the help of this stimulation. Suppose if I take, I am having the voltmeter at here. Now if we can apply the potential of the 1.5 volt. So let me measure what is the battery potential. So the battery potential shows at here 1.5 volt. Okay. Now this C1 plate accumulates positive charge and the C2 plate accumulates negative charge. Suppose if I measure what is the potential difference between the C1 and C2. Now if you can call this as C, if C equal to 1.5, and the C1 here you can see it shows at the 0.5 volt. Now what about the C2? So if we can measure from between the C2 plates, and the C2 is also showing that 0.5 volt. And what about the C3? The capacitance between the third plates. Now the capacitance between the third plate C3 equal to, it is also 0.5 volt. Now what is the total potential? If V is the total potential, 0.5 at C, so if I can call this as a V equal to, if I can call this as the V1 and the V2 and this is the V3. So the total potential applied equal to sum of the individual potential at the each capacitor. V1 plus V2 plus V3. So here you can add up 1.5 equal to 0.5 volt plus 0.5 volt plus 0.5 volt, which equal to 1.5 volt. So we will write in the series expressions the total potential difference equal to sum of the individual potential difference. Now if you are curious to see what is the potential difference between the same plates which are the connected. Now I am connecting the potential on the second plate of a capacitor C1 and the first plate of a capacitor C2. If we connect, or you think like this, the question is why charge from this plate to this plate, from the negative plate to positive plate, why charge is not moving? Why charge is not flowing? If I represent that as plate B to plate A, why the charge is not moving? So to move charge, there should be potential difference, because if here you can observe at here, so here the potential difference between them goes to equal to 0. There won't be potential difference. If there is no potential difference in that connecting, so the charge won't flow, it cannot move. Likely if you can measure the same potential difference between the connecting plates at here. Connecting plates means one leg of the capacitor is connected to the another leg. So in this case, the potential difference between the connecting plates goes to 0. So that's why the charge cannot move between the connections. It always moves from the first plate to the last plate where we connected. So finally I can say that in the series, the total potential difference which equal to the potential difference of the sum of the individual potential difference. Now I need to write the expression for the mathematical expression. If Q is the charge, on the capacitance plates C1, if you can write the relation between capacitance and charge. So we know that the basic formula at here, capacitance C equal to Q upon by V1. So for the first capacitors, so C1 equal to, the charge is same, which we can write Q upon by V1. From this I would like to write the potential V1 equal to Q by C1. For the second capacitor C2, which equal to Q upon V2, which equal to V2 equal to Q upon C2. So you can add the C3, which equal to Q upon V3, which also equal to, you can write the V3 equal to Q upon C3. Now if you substitute these three values, so these three values, if you can substitute in the above expressions, the total potential difference V, so that is also I can write, since since C equal to Q upon V, therefore V equal to Q by C. So in the place of V, if we can substitute this value, and in the place of the V1 and V2 and V3, if you can substitute these three values. So this is the values we need to substitute in the place of V, and this is the V1, and this is the V2, and this is V3. You can substitute that in the above expressions. So let me take that expression as A. Now our final expression turns as, so Q by V, Q by C equal to Q by C1 plus Q upon C2 plus Q upon C3. So we will eliminate the common factor Q. We will end up 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3. So if the resultant capacitance, to get the resultant capacitance, so these terms we will call as capacitance in series. So I can mention that as 1 over C is as capacitors in series equal to the final formula 1 over C1 plus 1 over C2 plus 1 over C3. So the resultant capacitance value obviously decreases. Let's see an example. Suppose if C1 equal to C2 equal to C3 equal to 1 picofarad. So what is the series combination of C1 plus C2 plus C3? What is the C series? Now if you can substitute that at here. So first, to find out the C series, capacitance in the series, the formula is 1 over C1 plus 1 over C2 plus 1 over C3. Now the C1 value is given 1 picofarad, and here also C2 1 picofarad, and the C3 also 1 picofarad. So pico is 10 power minus 13. So first I need to take the LCM at here, C series. Now the C series value equal to, so here I can substitute that as 1 over C. 1 over C. Now 1 over C equal to, if you can do the picofarads, take it out as an LCM since it's having the value 10 power minus 13, or you can substitute that as, you just take out the common of the picofarad. If I can take it out 1 over picofarad as a common, so I can get inside the 3, 1 by 1 plus 1 over 1 plus 1 over 1, so the total value goes to 3. Now if you can do the cross multiplication, so if you can do the cross multiplication and we can substitute the values of the picofarad, so we can get C equal to 1 over 3 picofarad. So the capacitance series which equal to 1 over 3, if you can write that 0.33 picofarads. So that's the same example we were seeing at here. If the capacitance of a capacitors, so each capacitor having the value of 1 picofarad, C1 equal to 1 picofarad, and the C2 equal to also 1 picofarad, and C3 also 1 picofarad. Now what is the total capacitance? So here you can see the total capacitance value. So C in series combinations, the total capacitance value given that 0.33 times 10 power minus 13 picofarad. So finally in series combination, the total capacitance value decreases. Likely we will see the parallel combination.